So our next speaker, unfortunately, not due to his own doing, couldn't make it here due to administrative difficulties, but fortunately we have Zoom. So we're very happy to have Graeme Wilkin, who will talk about the Morse complex on singular spaces.
Yeah, great. Thanks, Dan. And thanks to all the organizers for the invitation to give a talk here. It's really a great honor to have the chance to talk at this conference, and also to be a great honor to be one of Karen's mathematical grandchildren as well. So yeah, as Dan said, unfortunately, I wasn't able to visit in person due to circumstances beyond my control. But we do have Zoom, fortunately. But I'm sure after 2 years of Zoom, everyone would prefer an in-person talk. So hopefully next time I'll be able to visit in person. So we've heard a lot about Karen's work in different fields in the other talks. So in my talk, I'm going to talk a bit about her contributions to Morse theory. So first, before we begin, I'll just mention the philosophy behind Morse theory, that really it relates two different fields of mathematics. One is topology and the other is analysis. So the idea is if you have a smooth function on a manifold and that function has certain nice properties, then you can relate the topological invariance with the analysis of the function around the critical points. So for example, you might have some manifold that you're interested in. You want to compute topological invariance, and you might have a nice function that you know a lot about. You can use Morse theory to compute topological invariance in that way. Or conversely, you might have a manifold that you know a lot about, or you know something about, and you might have a function that's really interesting, but you don't know much about it. So for example, you might want to find critical points of some variational function, and people have used this. For example, Morse's original motivation was to prove existence of geodesics on manifolds. So these ideas have been applied to solve many interesting problems in topology, geometry, and analysis. So just some background. I'm always embarrassed by this because I know there are a lot of experts in the audience, but I like to start from the beginning and then I'll move forward pretty quickly. So this is the basic example from Morse theory that, we start off with an example like a torus. It's a simple one that we can draw. We have the height function that I've drawn here, and we have 4 critical points on the manifold. And the idea of Morse theory is that you can relate, if you imagine filling up the manifold with water up to a certain level, as the water rises, the topology up to homotopy type, at least, of that level set only changes when you go past a critical level. So if we keep filling with more and more water, then when we hit this critical point here, the topology will change, and then we'll put more water in the manifold. So if we fill it up like this way, we can see that the topology of MB is different to the topology of MA. So I'd like to make this precise, and this is exactly what the main theorem of Morse theory does. So the key thing that makes this work is the Morse lemma. So if you have a non-degenerate critical point, so the Hessian's non-degenerate, and the index, the number of negative eigenvalues or negative dimension of the negative eigenspace is lambda, then we can find nice local coordinates so that it looks like a standard saddle point around that critical point. So with that in hand, the main theorem of Morse theory tells us that we can use the gradient flow of F to make that the statement on the first slide more precise. So if there are no critical values in between 2 levels, so I'll just draw another level here, call it say C, then MC is all the points below that. We can flow down like that onto MB. And in fact, we can show that MC is diffeomorphic to MB. If there is a critical value in between the 2 levels, so here we have a critical point here corresponding to a critical value, then when we flow down, what we can do instead is flow down to attach, say, a handle like that. We can do this just by modifying the function. So I'll draw this so it looks smooth. And then it turns out that MB is diffeomorphic to MA with a handle attached. And then the local coordinates of the Morse lemma allow us to retract onto this unstable set of the critical points. So all the points that under the gradient flow up to this critical point. Okay, so that's the idea of the main theorem of Morse theory. So that is the first thing you read if you read a book like Milner's book on Morse theory. But as I said on the first slide, there are lots of interesting examples. In particular, a lot of those are on infinite dimensional spaces. So the picture I drew is compact. The theory works the same way if F is proper, but we're excluding lots of interesting examples by doing that. So Morse's original motivation is to study the path space. So if you have 2 points in a manifold, you want to look at all the smooth paths between them, or you could maybe look at the CK paths between them. And so on this path space, this is infinite dimensional, what we have is this natural energy function. So this action integral just by integrating the square of the tangent vector along the path. And it turns out that the critical points of that function will correspond to geodesics. So understanding the critical points will tell us about geodesics on the manifold. So going back to the first slide, the philosophy is if we know something about the path space, for example, if we have a manifold with a nice metric, like the round metric on the sphere, we can write down, or we can describe explicitly what the path space looks like. And then maybe you have a metric on the sphere which is not nice. For example, I remember once I was flying to a conference, this is a few years ago, when that volcano in Iceland was erupting, and all the airlines had to detour around the volcano. So the shortest path from the point of an air pilot was not the standard geodesic on the round sphere, but in fact a different one. So we have this perturbed metric, and we want to know if there are geodesics of certain length or arbitrarily long geodesics on a manifold with a perturbed metric like that. Okay, so we can compute the index by counting conjugate points along the geodesics, but the issue is that the path space is infinite dimensional and the function's not proper. So the previous statement of the main theorem doesn't apply directly, but we'd like to apply something like that. So one solution, for example, if you read Milner's book, you can see how to approximate the path space by finite dimensional manifolds, in which the main theorem does work. It'd be more satisfying to do Morse theory on the infinite dimensional path space directly. So what we need is some replacement for the properness of the function. And this is exactly the Palais condition C. So I've written down the statement here. The idea is that if you take some sequence of points where the function's bounded, but the gradient of the function at those points converges to 0, or maybe it's just not bounded away from 0, so it converges along a subsequence, then it says there's a critical point of the function in the closure of that set. So if we have that with the condition C in hand, then under these conditions here, an analog of the main theorem of Morse theory works. So this is stated in terms of handle attachments and diffeomorphisms, as in Palais' famous paper, Morse Theory on Hilbert manifolds. But the idea is essentially the same as the previous one. So it's condition C that makes all of this work. So Karen Uhlenbeck's first contribution to Morse theory was to show that this theorem extends in the more general setting of Banach manifolds, where you don't have an isomorphism of the tangent space with a dual necessarily. And then more interestingly, this is something that came later, you could ask, does condition C hold for the Yang-Mills functional, which we've seen already? So if you have some principal bundle on a compact Riemannian manifold, compact structure group, then we can write down the Yang-Mills functional as the square of the L2 norm of the curvature. And then you can ask, does condition C hold for the Yang-Mills functional? So even before the work of Uhlenbeck, we knew that this it was not true. So the first reason it doesn't hold is because the function's invariant by the infinite dimensional gauge group. So that means that the critical sets are infinite dimensional. And in particular, if you look at the minimum here, you can take some sequence along a gauge orbit that doesn't converge to anything. So condition C will then fail in this setting for simple reasons. So really the key is, you could then ask the question, does condition C hold modulo the gauge action? And this is where the Uhlenbeck compactness theorem that Cliff Taub's explained in his talk comes into play. So when the dimension of the manifold is greater than 4, or greater than or equal to 4, then it turns out that there are sequences of Yang-Mills minima which become singular, and so they can't converge to a limiting connection which is smooth. But it turns out that that's the only thing that can happen. So Uhlenbeck compactness gives you some control over the type of singularities that emerge in this case. So when the dimension of the manifold is 2 or 3, there's no bubbling. So this follows from the compactness theorem. And then 2 of Karen's students, George Daskalopoulos and Johan Rada, together showed with different papers, but when you combine the 2 results, the Yang-Mills flow converges to a smooth limit. And this was important because previously, a few years beforehand, Atiyah and Bott had studied the Morse theory of the Yang-Mills function on Riemann surfaces, but in a stratified sense using algebraic geometry. So this, these 2 results together essentially filled in the analytic details behind this theory. And then, so this was published before those papers. So Cliff Taub showed that you can recover Morse theory when the dimension of the manifold is 4 if you take bubbling into account. Okay, so those are important contributions for the Yang-Mills functional, and a model example of the Yang-Mills functional works in finite dimensions. So, for example, you could look at a problem in algebraic geometry is to study a connected reductive Lie group acting linearly on either an affine space or a complex projective space with either the Euclidean metric or the Fabini-Studi metric. And then you can ask if the maximal compact subgroup is Hamiltonian with respect to the standard symplectic structure. Then we have a moment map for that action. And then if you pick a subvariety, which is invariant by this group action, the action of this complex group up here, then we can ask about this function. So f is the norm square of the moment map, and then try and understand what the Morse theory looks like in that setting. So something going back to Atiyah and Bott's example, they showed that on a Riemann surface, the Yang-Mills functional corresponds exactly to a function that looks something like this. It's the moment map for the infinite dimensional gauge group acting on the space of connections. Something I worked on in my thesis under George was the Morse theory for space of Higgs bundles, certain low rank cases. So that's a singular space where, again, we have a setting that looks something like this. So in this class of examples, I like to include things like Nakajima quiver varieties or moduli spaces of quivers with more general relations in this setup. Okay, so this is all motivated by the questions previously. One thing I should say about these examples is that the critical sets are non-compact. So for the same reason as before, we'll need some replacement for condition C. But a good thing about these examples is, as I mentioned before, for the Yang-Mills flow, these moment map flows are very well understood. So they have a lot of nice properties, and we can use that in developing a Morse theory on these spaces. So here's a description of the type of functions we're looking at. So I should warn you at the beginning, I have to confess this is a little embarrassing. All these pictures are of the torus. So they're supposed to be of singular spaces and different types of spaces, but we only have so many dimensions to work with. So almost all my pictures are going to be of the torus. So hopefully you can imagine this could be some singular space. And the idea is we have some energy function on that space. So I'll draw it as the height function, as we did before. And on the space, what we're assuming is you have some gradient flow. So it lives inside some manifold on which you can define the gradient. And if you pick an initial condition in this space, there's some small neighborhood, both forwards and backwards in time, on which the gradient exists. And the conditions later on will show that you need to be able to extend it a bit further than that. But the idea is, in order to avoid having to study the singularities of this space in detail, what I'll do instead is just think of all the vertical lines that are defined by the gradient. So some of these vertical lines will have to stop at some point. So for example, here's a gradient line that will stop at a critical point, or they might stop down here at the minimum. But in between there, we can essentially not really foliate the space, but we can fill up the space with these vertical lines. So this is all we have. And then we want to add some extra conditions in order to make the Morse theory work. So this is the question. So in this setting, can we find some conditions in which an analog of the main theorem of Morse theory works? Okay, so as I said before, the Palais condition C is not satisfied in many of these examples of interest, essentially because the critical sets might be non-compact. But something we do know is we know the critical sets very well for these moment map functions. We know something about the gradient flow of the function near the critical set. So instead, we can impose some weaker conditions. So if you go back to Palais' paper, where he introduces condition C, you'll see that these are consequences of condition C. So the first one is the critical values are isolated. So here's a critical point here, and here's a critical value. And so that's quite a simple condition. And then the next condition essentially just says the flow that I showed before. We said we're assuming it exists. Essentially nothing bad can happen here. So if you start flowing, you flow down, you might go out the bottom of the or the this subset of the singular space. And if you flow up, you might go out the top, or you might get hung up on a critical point. And essentially these are the only two things that can happen. Either you flow out or you flow to a critical point. So the thing you want to avoid in these situations is you want to avoid going off to the boundary of the manifold. And condition C is designed to avoid that. So if you don't have condition C, you need to impose some condition that says you don't flow. Again, you'll have to use your imagination here. You might flow sort of off all the way out to infinity and never converge to anything. Or you might sort of flow around and sort of circle around, but maybe no subsequence converges to anything. So these are things that you want to avoid. And this condition 2, this is essentially something that excludes those possibilities.
Can I ask you a quick question?
Yeah, sure. Yeah, of course.
So you've got the T plus there, and I'm trying to interpret it. Do you mean the little t in the next expression is plus or minus T plus? Just trying to figure out what the condition.
Oh, yeah. Sorry, yeah. So T plus greater than 0 such that this is true for all T greater than T plus. Yeah, thanks. Sorry for it. The problem with giving a slide talk is that everything's written in advance. So if there's a typo, then you're stuck with it. But yeah, that's right. Yeah, thanks for pointing that out.
No worries.
Yeah. Okay, so this is condition 2, essentially a replacement for condition C. And then the third condition is that we need some replacement for the Morse lemma. So we need to know something about the behavior of the flow around the critical points. So we can't have something arbitrarily bad happening. So just for notation, I'll define the unstable set. So these are all the points that flow up to the critical set. And the stable set, the points that flow down to the critical set. And so if we pick the unstable and stable sets of some critical set here, then what we want to do is impose some condition that says that if we start near the critical set and we flow down, then we can't wander too far from the unstable set. So I think this is best described with a picture. So, so we have some conditions here. So we pick some neighborhood of the unstable set down below the critical set. We have some neighborhood of a critical point. So in the picture here, this is the neighborhood of the critical point, which I've colored in yellow. This is the neighborhood inside the level set. And essentially what this condition says is that if we flow down, then we flow down into the, and over the back of the saddle point, the same thing happens as well. We flow into this set U. And then if you shrink the set U, so you can make it maybe smaller, well, you can manage that just by shrinking the set V. And then we have to flow into some set here. So this is something that works for hyperbolic flows. And essentially this is saying that the flow sort of looks like a hyperbolic flow near the critical points. Okay, so something to avoid here is that you can't start, if you start close to the critical set, then you can't just suddenly diverge away from the unstable set. So for example, if you're back on the smooth manifold case in some infinite dimensional manifold, then maybe the negative eigenvalues of the Hessian might converge to 0, which would mean that along some path, you might have flow lines that look very close to horizontal. Okay, so we want to avoid that sort of thing, and we can, because that works for these moment map flows in any reasonably behaved flow. And then finally, we need some condition on the singular space. So I haven't said anything about the singular space other than that we have these vertical lines. So essentially we want to be able to flow down, but then we also want to be able to retract across as well. So if we go back to the previous example, we know that we can flow into this set here, U, if we make our V small enough. And then once we're in the set U, we want to be able to flow across to the unstable manifold. Okay, so maybe I could just draw another schematic of what U might look like. So for example, U could be some singular set that looks something like this, and we're retracting this way. Or maybe U might be some neighborhood of that. So I'm just going to go up a dimension and say that U is some neighborhood of this set, and this is the intersection. There's 3 lines of the intersection of the unstable set. And then you want to retract in towards this set like that. So once again, you can do that. This is more a topological statement here. For example, if you have some triangulations, then you can do this explicitly. And then more generally, if you have Whitney stratification. So if you have a Whitney stratification of the level set down here, and the intersection of the unstable set is a substratification. Okay, so with these 4 conditions, we can prove an analog of the main theorem of Morse theory. So this is from a few years ago. So we take some real analytic manifold and an analytic function. So that means that the has nice flow properties. Essentially, this condition 2 works in that setting. And then you have some subset preserved by the gradient flow. Subset could be singular, but we know that conditions 1 to 4 hold. Then in that setting, we have an analog of the main theorem of Morse theory from before. So either we can flow down from one set down to the next set if there are no critical points, or if there's one critical set, then the topology changes, and it changes by attaching something that looks like the unstable set of the critical set. So that's nice, but you can prove anything if you attach enough conditions. So of course you could just make the conditions really strong, and then your theorem would be true but useless because there are no examples. So theorem 2 says there actually are a large class of examples on which this theory works. So in particular, the norm square of a moment map on a variety satisfies these conditions. And then the third theorem, this was joint with Marcus Flaum. So of course the dates here are a bit strange just because it may take a few years for things to get published. But this came after the first 2, and the idea was you wanted to do everything equivariantly. So we showed that if there's a compact Lie group acting on a singular space and the function's invariant by that, then all these deformation retracts can be made to be equivariant with respect to the group action. Okay, so that's good. So it says that we have a main theorem of Morse theory in this setting. So what we'd like to do is develop a Morse complex, as I said in the title. So I'll just go back to theory that's well known, has been well known for a few years. So suppose we have a Morse bot function on a compact manifold. So critical sets of manifolds, and they have at the critical set, the eigenspaces of the Hessian are either tangent to the critical set or they're positive or negative. So in this case, we have the gradient flow induces a filtration of the manifold. So all the critical levels, you can look at the points that flow down to that level or below. So that fills up the manifold in this way. And the Morse bot condition means that on the first page of the spectral sequence, which is made up of terms like this, we have the main theorem that says that we can reduce this to some local calculation around the critical set. And then the Thom isomorphism says that that's just a shifted cohomology of the critical set itself. So if we have a Morse bot Smale function, so in addition, we're assuming that the stable and unstable manifolds always intersect transversely. So this is not always the case, as I'll show you in a few minutes. But in this nice setting, then we can construct the differentials and the cup product on this Morse complex. And we can do that by understanding spaces of flow lines between the upper and the lower critical sets. So the idea is we take some cohomology class down here, pull it back to space of flow lines, and then you can operate on it, maybe by taking cup product with something coming from the manifold, and then you can push it forward down to the upper critical set here. So here the U means upper, and here the U means unstable. Okay, so those are things we can do. And of course, the push forward is just integrating along the unstable set. So this is something that's well known. So for example, if you look in, say, Bott and Tu's book, this is studied in detail. So I'll just do an example just to illustrate the theory. This is a good motivating example. So if you take S3 and you have a function, here's an example height function on that. We have two critical sets, so a minimum and a maximum that look like a circle. So I've drawn the maximum here. So really the function in this case looks something like that. The function's increasing in this direction. And the projection, well, so firstly, the space of flow lines looks like a torus. So we have this two torus here. And the fibers of the projection, so if you pick a point in the minimum, then the fiber looks like this circle going one way. If you pick a point in the maximum, fiber looks like a circle going in the opposite direction. So that means if you pick, say, a one form, so for example, you could pick a vector field just determined by rotating the lower critical set, and then a one form dual to that using, say, metric or something. Then if you pull that back to the torus here, then along each of these red fibers, that integrates to something, which then determines a function on the upper critical set. And that's exactly how the differential is constructed in the Morse complex. So down here, we've got, if you look at the Poincare polynomial, down here, we've got dimension 1 in dimension 0, and then dimension 1 in dimension 1. And then up here, the contribution, the index is 2, and then the Poincare polynomial of the circle looks like this. And essentially, what this does is it says that the t from here cancels out the t squared up here, and we're just left with the cohomology of the three sphere. Okay, so that's how the differentials work in this case. So the idea is you want to do this pull back, push forward construction. Okay, so what does that look like in general? So in general, in terms of a spectral sequence, we can always do that. So we have this relative cohomology groups. We can just take the map from the long exact sequence of this pair map that into this cohomology group, and then look at the long exact sequence of this pair and map it into this cohomology group. And that combination gives you the differential in the spectral sequence, which corresponds to exactly this pullback push forward construction that I mentioned on the previous slide. So that's the construction, and you can do this in singular cohomology as well. It doesn't have to be Theorem cohomology, as in Austin and Brahms' paper. So the spectral sequence construction works in singular cohomology. But a key to this, as we'll see in a minute, is the transversality. Okay, and then you can do the same thing with the cup product. So I won't go into too much detail here, but I'll just say that after you've pulled back, you can then take cup product with some cohomology class coming from the ambient manifold, and then you can integrate that, push that forward down to the upper critical set as well. Okay, so as I said before, the moment map examples from before are not more spot. These are minimally degenerate. This is something that Kerwin studied many years ago, and turns out to be true for the Attia and Bott example I mentioned before as well. So I'd like to understand how this construction works in this setting. First on a smooth space, and then after we do that, we want to restrict to a singular space, the motivation being these quiver varieties that I mentioned before. So the picture I drew before, essentially this is sort of how it all works. So I won't go through all the details of this diagram here, but maybe I'll just say what the different levels look like. So this comes from the spectral sequence, this top row. So this is purely algebraic. And then once you have the main theorem of Morse theory, then we can map everything down to this second row here. So essentially the relative cohomology groups localized around the critical sets. And that also works for the critical sets as well. And then finally, to make this construction on the space of flow lines work, then we need transversality. Okay, so what does that mean? What does it look like? So the reason is, if we pick something, so we suppose we take the unstable set of this lower critical set, we want to be able to lift it up to the space of flow lines. So it should look something like a normal bundle to the space of flow lines. And then if we want to restrict it to the intersection, so restrict that normal bundle to the intersection, then that should look like the normal bundle of the intersection inside this unstable set. So again, unfortunately, we've run out of dimensions to describe this properly. So I'll just draw another picture here. Here's the normal bundle of one set. And then when we look at the intersection, that normal bundle restricts to the normal bundle here, or at least it's isomorphic. I mean, the metric, normal bundle depends on the metric, which may not match up nicely with the manifolds, but that's the idea, at least it's isomorphic. So if they intersect transversely. So that's what makes everything work in the previous diagram, or at least that last step with the flow lines. And the same is true for the cup product as well. So I won't go into much detail on this slide either, but just to say, essentially we can do this pullback, push forward construction from before. And the main theorem allows us to reduce to spaces localized around the critical sets. And we need transversality here. Okay, but unfortunately, transversality fails in the examples we're interested in. So as I said, we have this example of representations of a quiver with relations. So I didn't define what this was, unfortunately, just due to reasons of time, but you can imagine you have some vector space and some function on the vector space. Critical sets may be non-compact. You want to restrict to some singular subset. So some subvariety here, which fortunately is contractible, so we know what the cohomology ring looks like. Critical sets are really interesting. So for example, in certain cases of these quiver varieties, this was theorem of Kronheimer and Nakajima, it showed that these correspond to moduli of framed instantons on four manifolds, certain four manifolds. And this pullback push-forward construction to the flow lines corresponds to something that looks like Nakajima's constructions in geometric representation theory. So what we'd like to do is apply the theory that I just described, the Morse bot theory, which is well known, on this ambient CN, this manifold here, and then pull everything back to the singular space, just using the inclusion. But unfortunately, the moment map function is not Morse bot, and the stable and the unstable sets don't intersect transversely. Okay, so maybe I could just describe this failure of transversality here. So suppose now, so we drew this previous picture of these two lines intersecting, but the ambient space was R2. Here in R3, you have this normal bundle, which is two-dimensional. But when you intersect the two manifolds, you have some two-dimensional normal bundle, but the normal bundle within the intersection is only one-dimensional. Okay, so this is what goes wrong. And as you can see, it's not, it's not a disaster. It's not as if we have some funny intersection here. It's just that the ambient space is too large, essentially. So this is something that we can recover. Essentially, what we have is this quotient bundle, which you can think of as the normal inside the normal bundle. And if we can compute the Euler class of that quotient bundle, then we can augment the previous diagram. So of course, the details of the previous diagram, you may have forgotten those, but if you remember that we had the main theorem, and previously we had transversality to relate everything to the flow lines. Now what we want to do is we want to pull back space of flow lines and then take cut product with this Euler class here. So if we do that, then we can recover the cut product in this setting. And the point here is that the Euler class is computable. So we can actually write down what it is in terms of a polynomial in this polynomial ring. And also, I didn't really just say which classes we're cupping with up here, but essentially this cut product with the Euler class doesn't interact with the cut product with the classes that I'm interested in. Okay, so that's good. So we can recover the cut product on the ambient space in this way. All right, so what's the reason for doing this? So the motivation was behind this was that Nakajima, in a series of papers in the 90s and early 2000s, constructed representations of certain algebras. And he did this by this convolution action. So this is in Borel-Moore homology, but the idea was exactly the same. Take a class here, pull it back to some intermediate space, which in this case is a Hecker correspondence. And then you want to push forward down to this this other moduli space here. So a theorem from a few years ago is that for moment map flows in spaces of quivers, the Hecker correspondence is homeomorphic to a space of flow lines. So you can think of this as a space of flow lines inside some singular space. And there's an analogous theorem that works the same way for the Yang-Mills Higgs flow. Of course, there's more analysis in the Yang-Mills situation, but the idea is the same. So this space, which is interesting to the algebraists, is the same as the Hecker correspondence, or the same as the space of flow lines. So then finally, what's the goal here? So the idea is you want to take cut product with a certain class. So I'm just going to call it omega here. Essentially, it's hard to explain all the details, but the class we want to take cut product with is the Tom class of some submanifold that sits inside the normal bundle up here. So it's something we can write down, but not explicitly in the polynomial ring, not yet. And then the idea is when you pull everything back to the singular subset, then that corresponds to the convolution in Nakajima's picture. So, so that's a theorem. And then what we'd like to do is try and use that to understand Nakajima's constructions in more detail. So this is a Morse theoretic approach to a problem that's sort of seemingly algebraic or seemingly geometric. And as we've seen along the way, a lot of Karen's contributions to Morse theory and contributions coming all the way down the family tree from Richard Palais to Karen to George, and then have contributed in this direction. So I think that fits the theme of the conference, and it's a good place to finish. So thank you.
Thank you for the very nice talk. Questions? Okay, if not, let's thank Graeme again.
Okay, thank you.